Hi, Professor. This is Srinivas Teja. Previously, my teammates Ajay and Siva explained how the slicing is done and how we assign values to the robust variable. And in this slide, I am explaining the size of the slices produced. For the example program used in the case study, a robustness slice construction algorithm should be able to produce the ideal robustness slice. That is the simplest possible slice, which is the final step below. That is, we will see the final step, revealing immediately that the original program is not robust. Providing transformation rules which would produce such a slice is less difficult than it seems. In order to move from step 4 to the final step, previously we've seen the step 4 and now we'll see the final step. All that is required is a transformation rule which exploits the fact that the Boolean expression of a while loop is true at the outset of the execution of its body, and that the result of the Boolean operation, which is a logical operand, is false whenever either operand is false. Of course, due to the fact that robustness is undecidable, because the robustness will change based on the variables, it will not always be possible to produce an ideal slice. Such as this example, we take the final step where the robust is equal to 0. And we use some more complex language semantics where the language small c is extremely simple. When we consider a language small c, which is a subset of C programming language suitable for resource limited microcomputers and embedded systems, and an implementation of that subset. Originally, the small c program is used for microcomputer systems, which is available for 70s and 80s. And this also useful for as an example, simple enough for teaching purposes. Whereas this small c was introduced by Ron Kane, which is in May 1980. And it is a retrogatable compiler. Porting small c requires only that the backend code generator and the library to operating system interface calls be written for the target processor. In this, we see some, although this is commonplace today, it is a very novel ideal at that time. His compiler generated assembly language for the 8080 processor. And sorry, Professor, previously I missed one slide, which is the table given in figure 6 gives the sizes of each program produced in the course of the case study, where size is the number of nodes in the program control flow graph. It is of the nature of the approach that the size of a program will increase as the result of side effect removal and the introduction of the pseudo variable robust. The hope is that in many cases, the simplification produced by slicing and transformation will yield a robustness slice, which is significantly shorter than the subject program. This will be an objective measure of simplification that can be used to assess the suitability of the approach on a case-by-case basis. We consider here the case-by-case basis, and the robustness slice, which will always be semantically very simple. We have seen so many in the previous slides, as it is merely concerned with storing one of the two values in a single variable. This alone may make the robustness slice easier to analyze than the subject program. The principal task for further work rests upon speeding the best transformation tactics with which to simplify the slice produced. Here we just simplify the slice because we get difficulties in that while preparing. It is upon the power of the slicing and simplification transformations that the applicability of the robustness slice approach critically depends. And previously I told you, like, the small c language is extremely simple, and the simplicity hides some issues which arise when a large subset of c is chosen. It is the small c is used only for minor codes, but not for the bigger ones. For example, when arrays may occur as the parameter to a function, The function definition need not specify the array bounds. Each call to the function can potentially pass an array of different length. Each call to the function can potentially pass an array of different length. We use different lengths in order to correctly assign to the pseudo variable robust. An extra parameter to such function definitions will be required, giving the length of the array parameter. Here we just assign some length to the array parameters. And however, this extra parameter may be introduced merely by defining another class in the definition of TA. Similarly, issues arise with the dynamically allocated storage and with the exploitation of the array pointer duality in C. And some related work we done for this is the Rosenblum has implemented in 1995 a preprocessor system called APP, which replaces the traditional C processor, because in the traditional C processor we cannot do the bigger codes, so we implemented this preprocessor called APP. In addition to the normal C preprocessor tasks, the APP recognizes comments of the form as containing assertions about the state of the program. An assertion takes the form of pre and post conditions at the functional level of abstraction. The preconditions capture the set of initial states in which the programmer expects a function's body to be executed. The post conditions capture the set of final states in which the function will terminate. So here the function will terminate in the final states. The two different post conditions are permitted, which is a promise of E, which delimits the set of admissible final states for the function body, and return I where E, which constrains the possible values returned by the function. And the assertions recognized by APP are introduced by the programmer and are checked at runtime by code added at source level by the APP preprocessor. We completely use now APP preprocessor to check the runtime and everything. The robustness slice approach, by contrast, does not require the programmer to add the assignment statements which capture the program's robustness. Rather, these are added automatically by the transformation function T. The programmer is then expected to analyze the robustness slice produced by slicing and information. David Flatter and his colleagues describe an extension of the C programming language in which assertions concerning inter alia robustness are automatically added to the C program to create a program which performs checks upon its behavior at runtime. The process of introducing checking code for the integrity of array indexing is almost identical to the process of adding assignments to the pseudo variable robust. The principal difference between robust C and the robustness slice approach is to be found in the way the self-checking program is used. Here we use some self-checking program to just check the robustness of the slice, and the robust C program is executed with invalid array indexes, causing the execution of the program to terminate with an appropriate error message. We terminate the program when we get an appropriate error message. Now my friend Vishwanath will explain the remaining part.
Hello, Professor. This is Vishwanath. Hello, Professor. This is Vishwanath. I'm going to explain my friend Vedha Teja has stopped the previous slide. I'm going to continue this part that this is not the case with the normal C programs, whereas Flatter and his colleagues pointed out, the existence of this form of defect may cause no fault to occur at runtime. The self program produced by T is not produced with execution in mind. Indeed, the checking program produced by T would have not observable exact other than an increase in execution time. Instead, the result of T is an intermediate step in between the production of simplified program, which abstract that the part of the program concerned with the robustness in the form of robustness slice. Robustness slice is not necessarily executed, but it is also analyzed by the programmer who has the benefit of considering the robustness characteristics of the original program in isolation. In this program, the only form of robustness considered is the integrity of array indices. In Flatter in 1993, Flat and his colleagues considered the wider range of robustness issues, including variable reference before definition, loop bound checking, and null point difference checking. I'm going to explain a simple loop fragments, which is pointed out by the Flatter and his colleagues in this slide. First step, we're going to take I is equal to 1, and then we're going to start with s as variable with starting with 0. We increment by taking the while loop as I less than maximum. Then what we do is we iterate with every time with an array index a of I. So we increment the loop I is equal to I by 1. The original program, what we done in the slice is we're gonna make the slice where the sixth part comes into place. What we done is we taken this entire thing from 3 to 6 as a slice. In the next step, slicing as a part of testing strategy. This slicing can be viewed as a way of choosing an arbitrary modularization of a program. Each module being formed with respect to the slicing criteria. Let me tell you about the slicing. Slicing or a program slicing is a technique used in software testing, which takes a slice or a group of program statements in the program for testing particular test conditions or cases that may affect a value of at a particular point of interest. It can also be used for the purpose of debugging in order to find the bugs more easily and quickly. Slicing techniques were originally defined by the Mark Weiser in 1993, and they were only static in nature at the same time. After Bogdan Coriel and Janusz Lasky introduced dynamic slicing, which can work for a particular execution of the program. It is a two types. First one is a static slicing, and the second one is dynamic slicing. These are explained as following below. The static slicing of a program contains all the statements that may affect the value of a variable at any point for any arbitrary execution of the program. Static slicing are generally larger. It considers every possible execution of the program. Coming into the dynamic slicing of a program contains all the statements that actually affect the value of variable at any point for a particular execution of the program. Dynamic slices are generally smaller, considers only a particular execution of the program. Let us see that by the example where we can write with the code snippet considering the int z is equal to 10 and int n, where we take the input from the user as n. Input sum is equal to 0. If n is greater than 10, sum is equal to sum plus n, else sum is equal to sum minus. So here the static setting for the variable is sum, because there is a conditions like if and else in the statement. So it considers both as at the same time. So from the let's look at the dynamic slice for the variable sum. Int n is equal to, when we take the input from user for the n, int sum is equal to 0. If n is greater than 10, sum is equal to sum plus. Next step, this would give a low coupling and high cohesion and so represent good design. The raising of an alarm, however, will depend upon the behavior of the parts of many sensor modules. In this case, the modularization of the overall system will therefore not simply test or analysis with respect to the alarm raising mechanisms. Slicing will effectively allow us to remodularize the program to create an alarm control module. So let's consider an example with a program where we write the program is equal to stat, and we derive these expressions. For example, for the stat, we find under the stat functions like out. We can find variables like out in expression while braced if, and in the out statement we can maximum think that the printf is one of the out one. And for the in statements, we take the scan because we take the input from the user. While is iterative loop, so we take the while. Now braced is one of the list. We can take the braced in the items as a list. If there is a if statement, we all know expression in the post s sign id number character, everything the variables that we consider to assign a value we derive in the expression. Binary operators like or less than or equal to, greater than or equal to, or equal to or not equal to, and positive minus. Expression list, expression and a variable list like variables, stat list like a stat, assign where we assign the values to the variables, array list id on the post or the like post increments, post increments like let's say I as identifiers, n is a numeric constants, b is a binary operators, p is a programs, c is a commands, h is a characters, s is a strings, lambda is a empty statement. Let's take t of p is consider is robustness is equal to 1, c of p in brackets. These all are the expressions that we can derive as an introspection transformation things and algorithms for creating a robustness. This hi professor, this next slide is explained by friend Avinash. He's going to take off here.
Hi, Professor. My name is Avinash Nalapuneni. My WSO ID is E238 and E435. And now I'm telling about algorithm, and it was briefly explained in 6 steps. Step number 1, remove the side effects of this process. And then in step number 2, apply T and forming a self-checking program. In step 3, slice the programming with respect to robust at its last line. And in step number 4, use a rule 2 and 3 and 4 and 1 to correlate assignments to robust. In step number 5, uses exams of 1 and 2 to simplify expressions involved in robust. In step number 6, repeating the steps 3 and 5 until slicing fails to delete any statements. And now there are some transformation rules to simplifying the slice. There are exemption 1 and exemption 2. In exemption 1, commutative of ands, and I can explain some about the communications of communicative assumptions mean they are, for example, there are 3 atoms related to the communication of adding. The first like called commutative law, and it's denoted by a equation like E1 and E2 is equal to then E2 and E1. For example, A plus B is equal to B plus A. Then exemption 2 is an implement of and there are 4 rules. Rule 1 is a conditional repetition, and rule 2 is a push assignment, and rule 3 is unfold assignment, and rule 4 is an removing assignments. Yeah, now I'm telling about sizes, the size of a case study of example of a stage in a transformation. There are a program and a flow graph and a description. The original program flow graph is 28, and the description of original program. And in step number 1, its flow graph is a 32, and the description the side effects of free version. And in example 3, in step 3, its flow graph nodes is a 33, and the conventional slides. Step 4, the flow graph is a 19. The description is a non-conventional slides. The final step is a flow graph as 1 and the best slice. The conclusion for this is conclusions are the robustness slides approaches, a combination slides, a meaning, preserving it transformation, and a pseudocode version introduction. 3 simple ideas for these conclusions are which allow us to form very simple robustness slices which capture the robustness of subject programs program from which they are constructed. Slicing simplification, the task of testing a program behavior with respect to particular subsets of its variable, and slices cannot as it stands. However, it's applied to the analysis of impacting aspects of the program behavior. This not denotes by a set of program variables. Then in such a case, it is possible to introduce like pseudocodes and a variable which capture the implied aspects of the program behavior, forming a self-checking program of kind of formed by automatic introduction of assumptions of testing robustness at various program points. Then applying a combination of a conventional slices algorithm, meaning preserving transformation to the self-checking program. A program is a producer the robustness slices which capture the of computation explicitity and its isolation. This approach cannot always produce a simple program. A single assign statement, since the robustness questions is undecidable. Therefore, the slicing and the simplification transformation must be redefined as far as possible in order to achieve the best possible approximation to the simplest program. Now, bearing in mind the close simplicity between the automatic introduction of assumption to check the executive characteristic and the introduction assignment to pseudocode and pseudocode variable description in this paper, it would be interesting to consider the possibilities of constructing the other form of robustness slices, which of the each could be used to explicitly capture one of these form of robustness behavior is a simple program, simplifying the program, and this is the conclusion for the this is the conclusion, and this is our presentation, professor, and thank you so much. Yeah.